uncertainty that is present in the model. Right, of course, there's no need to spend too much time on this. I won't understand much of a time series if I just look at the numbers. I need to project these numbers into a diagram. Someone might say, excellent diagram. Why don't we use also a histogram? You can use a histogram if you like, but this won't tell you a lot of information because in the time series, as the words say, time is crucial. And the histogram won't tell you really a lot about time. The histogram is about frequencies. This is what a histogram is about. There's another technique that is very old-fashioned, which is stem and leaf tree, which is basically this. It's used in statistics, but it was used a long, long time ago. You might have heard of it. If you consider a sequence of numbers that you want to study, imagine these numbers have been given to you in a chaotic way. So you might sort them out in ascending order. Then you might project on this table two columns. So the first is called stem, the second is called leaf. And the stem will be, for example, the numbers between 4 and 10. Why between 4 and 10? Because if you pay attention, the first number, once you have sorted your list, is 44, and it starts with 4. The last one is 106, so you take 10, and then you say 4, 5, 6, 7, 8, 10. Then on the leaf column, you will just report the second digit of all the numbers started with stem equal to 4. So 4, 6, 7, and 9. There's nothing for 5. Then 6 again. There's 3, 4, 6, 8. 8 repeated is fine. And then you go. But again, this, what does it look like? This reminds me, this histogram, okay? It's again about frequencies. It's not really about time. So you might use this if you like, but it won't give you much information. For a visual inspection, we still use this kind of diagrams. This is your first approach, the first thing you should do. Right. By now you understand that the time series must be refined before you can really understand what's going on. Sometimes your time series might have a high degree of variability, so it might just have this behavior, okay? So there's not much you can understand. You might not see if there is a trend or if there is a seasonality and so on. Now, what do you do? Well, you do the same thing you would do when you see a colleague of yours who is very agitated. When you see someone very agitated, very nervous, what do you do?
Relaxing.
Calm down, man. Have a chamomile. Calma, oh, siamo in Italia, calma. Nessuno si agita in Italia. So we want to smooth our time series. And say, calma, calma. In Italian, we say, fly down. When you see someone very agitated, you say, fly down, which in English doesn't mean anything, okay? So it's something, the Italians sometimes take English words and they put them together and the meaning doesn't mean anything to an Englishman, but in Italian it takes some meaning. So we want to smooth, we want to relax the time series, no agitation. How can we do this? There are different techniques. The classic one, and maybe the economists know it, is called moving average. The moving average is just an extension of the average concept. How does it work? Well, you look at your time series, so this sequence of numbers, and you consider the average, but not the average of the time series, just a part of the time series. For example, the first three values. You start from the first three values, you calculate the average, then you shift of one value, and again you calculate the mean of the next three values. And you shift one, and again the three, you consider the average, and so on and so on. In this sense, is moving average, because you are sliding, you're sliding from the left to the right. You need to consider only one thing, this is up to you, is the span. Quindi la dimensione di questa finestra che scorrete, questa dimensione la scegliete voi. This is the span. Just to give a practical example, imagine you have some sales and you have the sales for every month of the year. The sales are reported in dollars. You decide to have a span equal to 3. It means that you are generating a new time series. So calculating the moving average implies you're generating a second time series, which is different from the first you were given. So these are the values. Okay, let's start. Span equal 3, super. You calculate 125 plus 145 plus 186. You divide by 3, and the result is 152. So this is the first value of your new or second time series. Then you move on. You are here, February. Now you have to consider February, March, and April. So 145 plus 186 plus 131. And you divide by 3, and the result is 154. Same thing here, March, April, and May. And you have this value. And so on, and so on, and so on. So it's not surprising, this is quite intuitive, that applying this moving average, you are calming down your time series. You are smoothing your time series. But, there's always a but. There's a problem. Can anyone tell me what the problem could be?
I have less value than before.
I lose a couple of values in this way. I lose, this second time series is slightly smaller than the first because I lose basically the first and the last. This is expected. So you can enjoy in applying this procedure to very hysterical time series like this one and applying the moving average, you might decrease the variability because this is what you want to do. This is what smoothing procedure or algorithm could do. Same thing here. Sometimes it depends by the time series you are considering. Just calculating once the moving average might not be enough. This is because the variability is so high that just apply this procedure once is not enough. You might apply more than once. Again, this is quite useful because by looking at this time series with some imagination, but this might be very subjective, you might say there's a trend, but you will see this only once you apply the moving average. So this is somehow a bit more clear. In essence, what is it, the moving average? The moving average is this. You are giving a weight to each value of your time series. This weight is equal to 1 for the span, for the sliding window you are considering, because the first time in here, I'm just giving a weight of 1 to January, to February, and to March. All the other month sales have weight 0. In fact, I only have 3 values in here. This means that the weight in here is 0, 0, 0, 0, 0, etc. In the second case, the weight of January is 0, but the weight of February, March, and April is 1 and 0 for the other months. Now, someone might say, fine, that means that the weights of this sliding window are all identical and they're all set to 1. But there could be another approach where the weight is different. The weight could be 0.25 for January, 0.5 for February, etc. So you give a different weight to the month. And this is what in this kind of filter happens. Now, the problem might be determining these weights. This depends obviously by the kind of problem, by the kind of time series you are considering. Keep in mind that you will never be a loner, a lonely wolf. Quindi quando voi farete questo lavoro non è che starete dentro una stanzina al buio da soli, no. You will always have to talk to a specialist. So if you are studying a time series that comes from the medical area, you should talk to doctors to understand what this data means. You should talk to the doctors if you can give different weights to these values. If you're working in a financial sector and you are not an economist yourself, then you just fetch an economist and you will ask, but can I give different weights for the sales in this month or not? Just to tell you that this, of course, it is a result of a certain study related to the time series and the problem that is connected to this time series. Now, I was saying before that the average in general is not a good index for a lot of reasons, but this is quite evident. Imagine this is your time series, so you have 200. 200, it might be an anomaly, it might be an outlier, or maybe it might be a legit value, but this will derange your calculations. But this is expected because the average is not a good indicator. Typically, you use the median. So the median is, well, I will not explain it because we've seen it already in the statistics class, is more fair, is more robust indicator. And you apply it exactly in the same way you apply the moving average. This would be the moving median. The N you see here is just the dimension of your span. M stands for median, obviously. It will be calculated exactly as we saw before for the average. The principle is the same. So if you just apply as a smoother a median, you would have this sequence of numbers for the case that we saw before earlier, which is this one. So as you can see, is rather robust because the 200 value is gone and it did not affect in any way my time series. But I'm losing values. This is something that was evident in that Excel file we saw before, is even more evident for the median. The problem might increase if you apply the moving average or the moving median more than once. And sometimes you might. It depends if the variability of your time series is very high, if your time series is very agitated, is very nervous. But that means that every time you apply your moving median or moving average, you will have some gaps. Now, this is not necessarily a problem. It's called information loss. It sounds awful, loss. But it's not a problem if your time series is huge. If you have a lot of data, you can easily neglect this. It is a problem if you do not have a lot of data. Because if you start to lose data, you do not have many, then you're in trouble. So there are different tricks you could take. For example, you might just, if you have a few gaps at the beginning and in the end, you might restore the first values here and the last values in here. It's just a trick. Most of the time it works. is a trick you have to make only if you have a few data. If your time series is extending for 1 year, 2 years, etc., you don't care about the information loss. It's not a problem per se. Okay, now we come to the joy of time series study. Basically, a part of determining the trend and the seasonality and trying to decrease the variability of your time series, you want to understand if your time series is stationary or not. Stationary means exactly what the word says. It means that the most important statistical measures do not change in time. Meaning that if you take just some windows, some time windows of your time series, the mean and the variance do not change. In this sense, the time series is stationary. In here, the slide is even say that it's strictly stationary, because there are some cases where you might have a condition for weakly stationary, but in general, the message is the time series is stationary if it does not deviate from there are no deviations from the average and the variance. These are the most two important moments that you study in statistics. So, visual inspection. This time series seems to be stationary. You might say that there is like a fixed value, and in general, if you have a peak, a positive peak, then you have a dip. So a dip should be the opposite peak. But this means that your average is not changing dramatically. So in line of principle, you might think that this is stationary. I was saying that visual inspection is the first thing you do, but since a visual inspection is subjective, you need also analytical methods to determine if your time series is stationary, or at least if there is enough evidence to say that it is stationary. So you might also run hypothesis tests in this sense. We will not see them today. You will see them in the class of time series. Now, if you look at this one, I find more difficult to say that this is a stationary time series because I can't really see a fixed point where all the other time series values revolve around. It seems here really there's no much stability. So I would say this is a non-stationary time series. Then what do? There are analytical methods to take a non-stationary time series into a stationary time series. So you can correct this problem. You need to do that because otherwise you won't be able to make any forecast. You cannot make a forecast on a non-stationary time series. Now, here you have different examples. And by applying a visual inspection, you should theoretically understand if the time series is stationary or not. Well, there are some rules of thumb to decide if your time series is stationary or not. In first place, you cannot have a trend. You cannot have seasonality. Now, let's see. For the B, the B, I can see immediately this is stationary. This peak you see is very likely an outlier. This is probably noise, something that shouldn't be here. It can even be removed in the analysis process that you make before anything. All the others have some problem. This is like a trend. This is like a trend. This is a trend with high seasonality. There are some seasonality possibly in here. The G case, which is this one, is assumed to be stationary. this is maybe a bit questionable. It looks like, but I wouldn't trust my senses. In here, certainly, I would apply some analytical methods. Then in here you have the whole explanation, especially with this controversial case. So I'll leave to you to read it. It's quite an interesting application, because I think is for a kind of animals, the lynx population. Right. Basically, we are looking for conditions of equilibrium. We want to look for stationarity because to apply any forecast model, our time series must be stationary. If it is stationary from the very beginning, thumbs up. If it is not, we need to apply some algorithms, some methods to make it stationary. That's the challenge. But nevertheless, we want a constant mean and a constant variance. These are the formulas you loved when you attended Professor Mazzocchi and myself class. Some of you have been exempted because you already suffered some time ago. But these anyway are the classical definitions of mean and variance for continuous random variables. So I will not spend too much time. And I won't spend much time also in the estimate of these two quantities. This is just the sampling theory that you loved so much during the first semester. It's just the estimator for the constant mean and the estimator for the constant variance in terms of sampling. But even here, I'm not saying anything new. What it could be more interesting is the concept of covariance. Typically, the covariance intervenes when you want to understand, when you want to compare two quantities. And these two quantities are statistically described by random variables, x and y. So the covariance is calculated in this way. You need to calculate the expected value of this difference for the x variable and the y, the expected difference between the y random variable and the average. And then you just use a normalization factor, which depends by the size of the data you are considering. Basically, you are trying to see if there's a covariance, so a kind of phenomenon that you can reproduce computationally. The worst case is when your covariance is close to zero, because it means that there's not much you can say about your data. This is just noise, just random values. There's no really something you can say between x and y. But in this case, you have a negative covariance. So negative covariance is still a covariance, or a positive covariance. You can be more precise and use the correlation. Correlation coefficient is just another way to consider the covariance, but the advantage is that you will have a number that is oscillating between -1 and +1. Again, 0 means that there's no correlation of any sort. If the correlation, on the other hand, is closer to -1, there's a negative correlation. It means that, what does it mean? What's the difference between a negative and positive correlation, apart from looking at the index, of course? What does it tell me?
The dependency between the variables. Like
if it's negative?
If it's negative, if one variable arises, the other ones have a lower value.
And this is still a correlation. If it's positive, if one goes up, the other goes up as well. Right. You wanted to calculate these values I was saying. I believe you know, you've seen the Pearson coefficient index, which again is working on the correlation. As I was saying earlier, we might be tempted to study two physical entities, by looking at the values that these two physical entities take, I might be interested in studying the correlation, but I might be tempted to say that one somehow is influencing the other. In other words, I might be tempted to say that there is also a causal correlation between these two entities. Maybe one is causing some effects on the other. This is quite natural, but statistics, unfortunately, is hardly intuitive. Typically, it's counterintuitive because our brain doesn't work in a statistical way. So, in general, there is this mantra, there is this rule, correlation is not causation. Why? Because correlation is commutative. So the correlation between x and y is identical to the correlation between y and x. But if you translate this in terms of causality, strange things happen. Because consider this example. We have this problem. We want to study the correlation between a certain diet, very caloric, probably there's a lot of sugar, and diabetes. And we make our calculation and we find there's a high correlation. It is 0.8. If you revert the variables, this still holds. Now, in the first case, you might say, it's really true that if your diet is made of sugar and pasticcini, e torte, e croissant, e la brioscina, e quell'altro, eccetera. But that means if you swap, you are forced to conclude that diabetes forces you to have a diet with a lot of sugar, which is not true. Absolutely not. This is an example where you have to be very careful in establishing a correlation, meaning that it's not enough to look at these numbers. Other example, if you go back in the 80s and you compare the data related to the sales of personal computers, and the 80s personal computers were booming. You compare this data with the number of people infected by AIDS, there's certainly a strong correlation. But of course, it's not that personal computer caused AIDS or vice versa. So you have to be very careful when you make this consideration. Right. Why we're interested in covariance and correlation? Good question, because when you look at your time series, all the values refer to the same time series, okay? It's not that you have different entities. There's only one entity. So what you're actually looking for is an auto-covariance and auto-correlation. So in other words, you're trying to see if there is a correlation and a covariance of the very same values of your time series. And this is interesting information for your models. So we do not have any more x and y, because now we're talking about our time series, and all the values are characterized by the same letter y. So we just define the auto-covariance described in these terms with this formula. Right, but how does it work? It means that you have to consider a certain lag. So your time series will be just made of numbers. Each one of these is a lag. If you consider, for example, a range of 1, but then your lag might be bigger, so it depends. But we could imagine a lag equal 1 for the sake of simplicity. Now, it means that in this formula, you're just calculating the autocovariance, for example, in pairs, the first and the second and the third and the fourth and the fifth, and so on. You are, and this is what the gamma of index k means, you will generate new values. because each pair, in this case, if k is equal 1, this is going just to be a pair, will produce a new number, and this is your autocovariance. So all these values, all these numbers you calculate, can be projected into a diagram because they form a function. This is the autocovariance function, or ACF in short. And this is a treasure of information when you project it on a diagram. There are some banalities. For example, for the very first lag for k equals 0, if you just calculate this formula, you just calculate actually the variance of your time series. This is for the autocovariance. You can extend this concept also keeping in mind the correlation, which is what we saw before, but you are applying correlation to your time series. So we speak not of correlation, but autocorrelation as well. The autocorrelation values denoted by the raw letter of the Greek alphabet of index k. So gamma is the autocovariance, rho is the autocorrelation. It's just calculated between the ratio between the covariance and the variance. And again, you develop a lot of values, because if this is a pair, you will have a first value for the first pair, then the second, then the third, the fourth, the fifth, and so on. This is called the autocorrelation function. And again, when you project it on a diagram, there are some considerations you can make. Just a couple of considerations. In first place, you do not have any unit of measure. So in this sense, the autocorrelation is dimensionless quantity. It's also symmetrical. So symmetrical just means that for each row k you calculate, you can also see the opposite in the negative quadrant. In this sense, is symmetrical. That means that computationally speaking, Python, when it calculates this diagram, can take half of the time because the curve is symmetrical. So it can just improve the calculations. Now, the typical ICF you would see, the autocorrelation function you would see, has this shape. So for the first lag 0, you always have a value of 1. This is expected. And you should see this behavior. So it will go down. And if you extend the numbers of lags, you should see that this go up again. But here something strange happens. Because if the time series is stationary, this fluctuation becomes very small and smaller and smaller and smaller and smaller. On the other hand, if the time series is non-stationary, you will see this cyclic period, you can call it cyclic, that will go forever. So there's no a smoothing process in act in this sense. This line, the dashed line you see here, is the confidence interval. And again, this might give you interesting information about the forecast model. For example, the ARIMA model that I'll mention in a moment requires the choice of 3 parameters. One of these parameters is determined by studying this curve, by studying the ACF. Right, from a theoretical perspective, the time series is infinite. It is a mathematical model, so you can imagine these numbers that goes to infinite. So what you really do is not just calculating the ACF, but you estimate it. This is what you do. You calculate an estimation, And the estimate is provided, of course, by the sample, basically the sample mean. It is applied in this way. So it keeps in mind the definition of autocovariance, and this is just normalized by the size of the period, the dimension, the time dimension you are considering. The final estimate of the correlation function that you obtain by a sample is determined just by this ratio here. So you have to take the CK you calculated in this step. So just your lag can be anything, but you divide by the same quantity for lag equals 0, which is the one that you calculated at the beginning. How many observations do you need to have a decent curve? That's a good question. By rule of thumb, at least 50, 60. But of course, the more you have, the better. It is hardly the case that you will work with small values. In general, you have a large time series, so your problem is actually the opposite. You have a lot of data. Probably in the class of Professor Pozzi, you will see also how to compress the data, because your time series might be so big that if you have to receive it for your customer, you might need a special machine and a special format. It is not something you send as an attachment in your email, because it could be, I don't know, a gig, 2 gigs. Keep in mind that the attachment of your email can be no larger than, I think 20 megabytes is the maximum. I never try myself. I received from students attachments of 18 megabytes, and that worked, but I think 20 is the maximum in here. So if you have large data sets and for whatever reason you need to transfer them to your colleagues, to me, etc., you better compress it or use different options. So for example, you upload it on Blackboard, I give you the widget and so forth. But there are some techniques to compress the data. There are different formats, and this applies to any data set, including time series. Right. As I was saying, there is a vast range of techniques to understand if a time series is stationary or not. Again, why do you need a stationary time series? Because you need to apply a forecast model. You cannot use a forecast model if your time series is not stationary. So, so far we just saw a few techniques. We might just plot our time series. We are so lucky that immediately we say, oh yes, this is stationary, it's evident. If it's not, we might plot the autocorrelation function. That might give us a more precise idea, because we should see this curve becoming smaller and smaller in time. But this is still a bit amateurish, maybe. We can see another technique called variogram. The variogram is just applying the concept of variance between the points of your time series. So variogram, variance, this is basically the concept. Specifically, if you just denote with G of index K, each one of these points is just is calculated a variance between the point, the observation of your time series. So the variance of the difference between the first two values, then the second and the third and the fourth, and so on and so on and so on. If you use K equal to 1, the lag equal to 1, it could be also something larger than that, obviously. But in this way, you are calculating the variance of each lag quantity of your time series. Again, you will define a formula that put together the variance of the generic T plus K lagger and the first, which is something vaguely similar to what you're doing here. So in the end, it's just another way to see the problem. This formula will give you a sequence of numbers, a sequence of values. Again, you can plot, and basically, sorry, this is what I want to see you. Basically, you see two behaviors. The first is this. You can see that there's no a real convergence. This curve, this function is somehow increasing monotonically. If this happens, so if there's not really a point where the curve converges asymptotically, this means the time series is non-stationary. Again, you determine this by visual inspection, I'm afraid. So you have to look at a plot. Python at this stage or any other language like our language will not help you giving you an answer like, yes, it is stationary, no, it is not stationary. You can just plot these values. Again, this will tell you the variance between the differences in your time series, and then you can normalize it. You can just normalize it by using this formula, which is just give you the mathematical justification for what I said. Because in here, I told you that this is a non-stationary because there's no asymptotical convergence. This is just growing monotonically, which is basically due to this way of calculate your variogram.
Per essere stazionario dovremmo avere un valore costante, un valore che si stabilizza.
Un valore che si stabilizza.
Ok.
Maybe there's even an example. Yeah. No, sorry. I thought there was. I will add an example of stationary time series where you can see that there is an asymptotical convergence. So you can claim that the time series is stationary. So to recap, what we've seen so far is the definition of a time series. We understand that time series can be somehow profitable for us because we are trying to predict the future values. To predict the future values, we need to know a few information first, which are concealed, they are hidden. These information are the trend, the seasonality, possibly cycles, and of course a stochastic component. Why we are looking for trends? Because to apply our forecasting models, our time series must be stationary. That means that the value of the average and the variance, the expected value and the variance, the first two moments, must be constant in time. So whatever range, whatever portion of time series I consider, I do not expect to see any variation in these two moments. If this happens, there are some techniques that will transform a non-stationary time series into a stationary time series. One technique, the classic one, is called differencing. It means that I take a generic point of my time series and I detract the previous value. And I do this for each value of time series. Then I will check again if the new time series I obtained is stationary or not. If it's not, I repeat this differencing approach. And I keep calculating these differences until my time series will get eventually stationary. This is the most classic technique you can use. But this is important because what I want is a stationary time series. Only then I can start to talk about forecast models. I'm nearly the end, as you can see. Which are these forecast models I can use? Well, the classic one is the simple moving average. Believe it or not, the moving average can be a predictor. it works exactly how I defined earlier. So you just define your span, which is like a slider you apply into your time. We know you calculate the average and you replace, therefore, your time series with this second time series. Why is it predictor? Because the moving average will reveal, or it should reveal, the trend. And the trend will give you an idea about the future behavior of your time series. If the trend is going up, it is reasonable to assume that even in the future, the trend will go up. Not forever, of course. The exponential smoothing, there's basically a formula quite complex you need to apply, and this will give you another forecast model, which is typically applicable in the case that your time series has a seasonal component. Seasonal components, for example, can be found in sales. Any sale has a seasonal component. If you sell items to farmers, certainly you will sell more when the farmer are working in the fields. Quando c'è la semina, evidentemente gli agricoltori verranno a chiedervi il materiale che gli serve. If you have a fireplace in your house, typically you will buy your wood in May, June, so that when November comes, all the wood is in the house, you can put it in your fireplace, etc., etc. Of course, if you run out of wood and you try to find the wood in January or February, you won't find it. Because this is a seasonal effect, okay? So sales are typically seasonal. So a time series that is a time series that has seasonality would consider as a forecast a smoothing model. It is called exponential because it applies the considerations I made when I explained the Hanning filter, in the sense that you give to each value of your time series a weight that is exponential. Why is that? Because imagine a strange time series. You plot your data, and your time series is doing something like that. So you might try to calculate the moving average. The moving average is a kind of predictor of itself because it's revealing the trend, and then it might do something like that. But then there's a change because here the points are going down, but the moving average will go on for a bit, and then it will start to decrease. So the moving average is not a good predictor if there's a lot of variability, because it will react badly to sudden changes. Why it reacts badly? Because, as I was saying earlier, it gives to each point the same weight. And this is not a good idea, because it means that it will keep a memory of these calculations. And this is not exactly what we want. Exponential smoothing is giving still a weight to these numbers, but a weight that is decreasing. So older points count less in this forecast model, which makes sense. I should forget the past at a certain point and be aware of any change. So in this way, exponential smoothing is much faster in reacting in these strange anomalies, and is preferred for seasonality. And then the name of the game starts here, ARIMA. ARIMA is the standard technique. You use a technique called autoregression and mix up other two components. One is called integrated. That is that technique I told you earlier. when you want to transform a non-stationary time series into a stationary one, you use differencing. So this I is a parameter that will tell you how many times you apply the differencing operator to your time series to make it stationary. And then the moving average, which is a technique slightly different compared to the one I explained earlier. But just to tell you, this is just a statistical technique. It's very powerful because it will change something that is non-stationary into stationary. So that is good. What is bad? The fact that ARIMA doesn't behave very well if your time horizon in the future is too wide. This is a limitation. The SARIMA model is just a variation of the ARIMA because they keep in account the seasonality. You might have a seasonality, you might not have it. And getting more and more sophisticated, the neural networks. Neural networks, which kind of neural networks? Well, you have to be careful in here because applying the classic neural networks model, you will have a horrible forecast. Why is that? Because the classic neural networks do not have memory. You need the concept of autocorrelation, autocovariance, moving average, and so on. These concepts have a certain memory of the time series, right? So good idea. You need neural networks which have memory. And in the last 25 years, there have been some modification to the paradigm of neural network to add the concept of memory. There are two models that have this property. The first is called the recurrent neural network, and the second is called long-term short-term memory. Why they have been introduced? These models, and I conclude, have been introduced not for the time series, but to solve another complex problem, which is the natural language processing. When you ask any artificial intelligence software to understand a text, there's a big problem because you might say, my name is Tommaso. This morning I woke up at 6 o'clock. Then I had breakfast. I got washed. Full stop. I got dressed. I went into the garage. I turned on the engine. Full stop. There was a lot of traffic. Then what happens is this. The software would completely forget who is the subject of this conversation because there's no memory. So it wouldn't be able to answer questions like who is the subject of the conversation, at what time the subject woke up this morning. These are questions too complicated because the text is so long that this information is lost in all the processing. So that's why these two kind of neural networks have been introduced. Not only they have a memory, so they will remember the subject, what he did, when, etc., but they can also forget. So it is possible to tune the amount of information that is memorized and what can be neglected. For example, in the text, there might be an information that says the car is yellow. This is completely irrelevant, maybe, and it can be forgotten. That will be all. Thank you very much, and see you next week. Thanks.